Welcome to our deep dives today. We're exploring the universe's stellar nurseries, molecular clouds, the places where stars are actually born. Think of it as a journey into cosmic creation, especially for those of you who are intellectually curious amateur scientists.
It's a fantastic topic. Molecular clouds are, well, they're special regions in the interstellar medium. What makes them stand out is their density and size.
Okay, density and size.
Right. Enough density that they can actually form molecules, mainly molecular hydrogen, H2, and they often appear as dark patches, absorption nebulae, because they block light.
So they're quite different from the rest of interstellar space, which is mostly, ionized gas?
Exactly. Much more diffuse, much hotter usually. These clouds are the cold, dense exceptions.
And the term stellar nursery, that's specifically for molecular clouds where stars are forming.
That's the key distinction, yes. When star formation kicks off inside one, that's when we call it a nursery. It perfectly captures their role.
But there's a catch to studying them, isn't there? Something about the main ingredient, the H2.
Ah, yes. Molecular hydrogen, despite being the most abundant molecule by far, is surprisingly difficult to detect directly, especially with radio or infrared telescopes.
Why is that? Seems counterintuitive if there's so much of it.
It's down to its structure. H2 is a symmetric molecule. That means its rotational and vibrational transitions. The little energy shifts that would normally emit radio waves are very, very weak. It just doesn't like to broadcast its presence.
Okay, so it's like it's hiding in plain sight. How do astronomers get around that?
Ingeniously, really.
Yeah.
We use a tracer molecule, carbon monoxide, COU. It's much less abundant, but it is asymmetrical and radiates much more efficiently at wavelengths we can easily detect with radio telescopes.
So the CEO acts like a signpost.
Precisely. The general assumption, especially in our galaxy, is that the amount of CO emission is proportional to the amount of H2 mass present. You measure the CO, you infer the H2.
But is that ratio always reliable? Does it hold up everywhere?
That's a really important question. Within the Milky Way, it seems to be a pretty good approximation, yes. But there's evidence suggesting this ratio might change in other galaxies with different conditions, different metallicities. So it's a powerful tool, but one we have to use carefully.
Right, context matters. Now, you mentioned these clouds are dense, but are there even denser regions within them?
Oh, absolutely. They're not uniform blobs. Inside molecular clouds, you find denser regions called clumps. These clumps are packed with gas and dust, and within them, even denser structures called cores.
Clumps and cores.
Yes, and it's typically within these cores that the magic happens. If a core becomes massive enough, its own gravity overcomes the internal pressure of the gas.
And it starts to collapse.
Exactly. That gravitational collapse is the very beginning of star formation.
It's amazing. These incredibly cold, dark places are the starting points for stars, which are anything but cold and dark.
It's one of the universe's great transformations, and figuring all this out has been quite a journey itself, tied heavily to the development of radio astronomy.
Let's talk about that discovery process. How did we even realize these things were out there?
It wasn't obvious at first. A key theoretical step came during World War II, actually. The Dutch astronomer Henk van der Hulst predicted that neutral hydrogen atoms, just single H atoms, not H2 molecules yet, should emit a specific radio signal.
Radio signals from hydrogen. That must have been revolutionary.
It was. Before radio astronomy, our view was limited mostly to visible light. This opened up a whole new way to perceive the cosmos.
And how did they actually find that signal?
Well, after the war, astronomers in the Netherlands did something quite remarkable. They repurposed captured German radar antennas, tuning them into some of the earliest radio telescopes.
Wow, talk about swords into plowshares.
Isn't it? They specifically set out to find Van der Hulst's predicted hydrogen line.
What causes that specific signal?
It comes down to quantum mechanics electron spin. In a hydrogen atom, the electron and proton both have spin. Sometimes the electron spin flips relative to the proton spin, moving to a slightly lower energy state.
And that releases energy.
Exactly. A tiny puff of energy at a very precise frequency, 120.405 megahertz, or as it's famously known,
The 21-centimeter line.
the very one. Finding it was huge. It was detected almost simultaneously in 1951 by two groups, Ewan and Purcell in the U.S., and Muller and Oort in the Netherlands.
So that was the first direct detection of atomic hydrogen gas in space.
Yes, the most common element. Mapping this 21-centimeter line across the sky gave us our first real glimpse of the Milky Way structure, including the spiral arms. The Leiden-Sydney map in 1958 was a landmark. And crucially, detecting atomic hydrogen paved the way for finding molecules.
How did finding H lead to finding molecules like H2 or CO?
Once astronomers knew where the atomic gas was concentrated, they could point their radio telescopes there and search for other, much fainter signals. The first success came in 1963.
What did they find?
The hydroxyl radical OH Barrett and Weinreb detected it in the radio waves coming from Cassiopeia A, a supernova remnant.
The first interstellar molecule detected by radio. That must have been incredible. Proof that chemistry happens out there.
A major breakthrough. Soon after, Weaver's team found OH in Orion and Cassiopeia as well. Then came ammonia, NH3, in 1968, formaldehyde in 1969. The zoo of interstellar molecules started to grow.
And molecular hydrogen itself. Was it found around there too?
It was identified, yes, but mostly indirectly. Because of that difficulty in direct detection we talked about, we saw its effects, its absorption lines in UV light from stars shining through clouds. But the real game changer for studying the nurseries themselves was carbon monoxide.
Back to CO.
Right. Penzias, Jeffords, and Wilson, the same team famous for the cosmic microwave background discovery.
Big Bang, guys.
The very same. They detected CO emission from a star-forming region in the Omega Nebula. CO, being asymmetrical, has those easily detectable rotational lines. It quickly became the go-to tracer for molecular gas where stars form.
And that led directly to finding the first actual molecular cloud.
It did. In 1970, Penzias' team pointed their telescope towards Sagittarius B2, a region near the galactic center known to be complex, and bam, strong CO signals. That was the first definitive identification of what we now call a molecular cloud.
It's interesting how their Nobel Prize work on the Big Bang's echo is sort of linked to this work on star formation building blocks.
Absolutely. It's all part of understanding the universe's composition and evolution. And since that first discovery in 1970, the number has just exploded. By 2022, we knew of over 10,000 molecular clouds.
10,000. That's incredible. So you know how to find them now. Where are they mostly located in our galaxy, the Milky Way?
Okay, so volume-wise, they're actually a tiny fraction of the interstellar medium, less than 1%.
Yeah.
But they pack a punch density-wise. They are the densest part.
Right.
The vast majority of this molecular gas isn't spread evenly. It's concentrated in a ring roughly between 3.5 and 7.5 kiloparsecs from the galactic center. Remember, a parsec is about 3.26 light years.
So tens of thousands of light years out
Yeah.
in the inner mid part of the galaxy. Our sun is further out, right?
Yeah, we're at about 8.5 kiloparsecs, so we're outside this main molecular ring. And this ring strongly correlates with the galaxy's spiral arms.
Oh, so they hang out in the spiral arms. What does that tell us?
It suggests they don't live very long. Material flows through the spiral arms, and if the clouds are mostly found in the arms, they probably form there and get destroyed or dispersed relatively quickly, likely on timescales less than about 10 million years.
10 million years. That sounds incredibly short for something so huge.
It is, on cosmic scales. A star like our sun lives for 10 billion years. These giant star factories are constantly being assembled and torn down.
Wow. And how big and massive can they get? You mentioned density.
They vary hugely, but a good example of a large one is the Circinus molecular cloud. It's estimated to contain about 250,000 times the mass of our sun.
250,000 suns worth of material.
Exactly. And vertically in the galactic disk, they're very flat. The molecular gas layer is typically only 50 to 75 parsecs thick, much thinner than the warmer atomic gas or the ionized gas layers.
Unless you count the HII regions.
Right. Those bubbles of ionized gas created by young stars inside molecular clouds, they naturally share that same thin distribution because that's where they form.
And on smaller scales, they aren't smooth either.
Not at all. Very clumpy, irregular. The gas is concentrated in discrete clouds and larger groupings called complexes. It's not a uniform fog.
Okay, let's zoom in on that structure and the chemistry inside. Typical densities again.
Average density might be around 10 to 30 particles per cubic centimeter. Which sounds like nothing, right? Almost a vacuum.
Compared to air, yes.
But it's way denser than average interstellar space. And these clouds, despite taking up little volume, contain about half of the total interstellar gas mass in the galaxy. Most of that gas is molecular.
And they don't have sharp edges, you said.
Correct. It's more like a fuzzy boundary, a transition zone, where the dense molecular gas blends into the surrounding atomic gas. These transition zones are often called envelopes, and they contribute to the irregular, often filamentary shapes we see.
Filaments seem to be a recurring theme. And dust, you mentioned dust earlier. How critical is it?
Absolutely essential. Cosmic dust grains act like tiny shields. They absorb and scatter the harsh ultraviolet radiation from stars.
Which would otherwise destroy the molecules.
Exactly. UV photons have enough energy to break molecular bonds, photodissociation. Dust protects the molecules, allowing them to survive and accumulate in these clouds. The amount of dust and radiation can vary, so the molecular mix inside a cloud isn't static.
So dynamic places. We know H2 is number one. CO is the tracer. What else is in there? You mentioned a zoo earlier.
Oh, it's quite a chemical factory. We've found things like methanol, ethanol alcohols, even benzene rings, the basis of many organic molecules on Earth, plus various hydrides and large complex molecules called polycyclic aromatic hydrocarbons, or PAHs.
Wow. The building blocks for more complex chemistry are forming in these cold, dark clouds.
It's pretty amazing. It hints at the potential origins of organic matter.
And inside these clouds, we have the clumps and cores again. Remind us of the difference.
Sure. The cloud itself is fragmented. Clumps are larger regions, maybe a parsec or so across, somewhat denser than the average cloud. They're like precursors to star clusters.
But not guaranteed to form stars.
Not necessarily, but within the clumps you find the cores. These are much smaller, maybe a tenth of a parsec, and much, much denser. These are the gravitationally bound nuggets that are actually collapsing or on the verge of collapsing to form individual stars or maybe small groups of stars.
Got it. And the 10 million year lifespan, what's the evidence for that relatively short existence?
A few things point to it. First, the ages of the youngest stars we still see embedded in or very near molecular clouds are typically in the 10 to 20 million year range. They haven't had time to drift away.
Okay.
Second, if you look at slightly older, massive stars, say OB stars, older than 10 million years, they're usually not associated with significant amounts of molecular gas anymore. The cloud they formed in seems to have dispersed.
So the stellar cuckoos leave the nest, and the nest disappears.
Sort of, yeah. Also, we don't see huge amounts of molecules frozen onto dust grains as ice, which you might expect if the clouds were extremely old and stable. It suggests things are quite dynamic, maybe turbulent, with gas cycling between atomic and molecular states relatively quickly.
Right, a constant churning. So if they're so short-lived, they must be forming all the time. How does that happen? And what ultimately tears them apart?
Good questions. Given their lifespan and the rate we see stars forming in the Milky Way, which is about, say, 3 solar masses worth of stars per year, we can estimate how much gas needs to be gathered into new molecular clouds.
To keep the star formation going.
Exactly. And the number comes out to something like 150 solar masses of gas being assembled into molecular clouds every year.
Whoa, that's a lot of gas gathering. How does it gather?
Two main ideas have been kicked around. One is that smaller clouds collide and merge, gradually building up into bigger ones.
Makes intuitive sense.
It does, but the problem is calculations suggest that process might be too slow to explain the number of clouds we see, given their short lifespans.
Okay, so what's the leading theory?
Gravitational instability. The idea is that within the general gas layer of the galaxy, some regions are naturally a bit denser than others, just by chance fluctuations.
Right.
Those slightly denser regions have a slightly stronger gravitational pull. They start attracting more gas from their surroundings.
Which makes them even denser.
And their gravity even stronger. It's a runaway process. Gravity amplifies those initial small density differences, pulling material together to form these massive clouds. The timescales predicted by these models fit the observations much better.
Gravity doing its thing. So the cloud forms, it gets dense, cores collapse, and then star formation itself starts breaking the cloud apart.
That's the irony. The cloud gives birth to stars, and the stars then destroy their parent cloud. Once massive stars ignite, they flood their surroundings with intense ultraviolet radiation.
The same radiation the dust was shielding against earlier.
Exactly. But now it's coming from inside. This radiation ionizes the nearby gas, heats it up dramatically, thousands of degrees, and causes it to expand outwards explosively.
Like popping the champagne bottle.
Precisely. They're often called champagne flows. This ionization and heating effectively evaporates the cloud from the inside out. And this happens relatively quickly, often, when only a small percentage, maybe 2%, of the cloud's mass has actually turned into stars.
So it's not very efficient at turning gas into stars in one go.
Not at all, typically. And besides the radiation, massive young stars also blow powerful stellar wind streams of particles that also push gas away and help disperse the cloud.
A double whammy of destruction from the newborns. What happens to all that dispersed gas?
It gets blown back out into the interstellar medium. Eventually, over time, it cools down. And once it's cool and dense enough again,
Gravity can grab it, and start pulling it into a new molecular cloud.
You got it. The cycle begins again. Formation, star birth, destruction, and recycling.
Okay, let's focus on that star birth part. Walk us through the collapse again.
Sure. It starts in those dense cores within the cloud. Gravity pulls the material inwards. As it collapses, the core fragments into smaller clumps.
Does it spin faster as it shrinks?
Often, yes. Conservation of angular momentum, like an ice skater pulling their arms in. These shrinking, spinning clumps continue to pull in more gas and dust from their surroundings accretion.
Getting denser and hotter in the center.
Denser and hotter, exactly. The pressure builds up. Eventually, the very center gets so hot and dense, millions of degrees, that nuclear fusion can ignite.
Hydrogen starts fusing into helium.
That's the moment. The energy released by fusion creates an outward pressure that pushes against the inward pull of gravity when those two forces balance.
You get a stable star, or at least a protostar.
A protostar, yes. It's reached hydrostatic equilibrium. It's not collapsing anymore, but it's often still shrouded in gas and dust, still accreting material onto itself, sometimes for millions of years.
And we can actually see these stages happening.
We can. The Taurus molecular cloud is a prime example. It's relatively close, only about 430 light years away, so we can study it in detail.
What do we see in Taurus?
Lots of young stars, particularly T Tauri stars. These are young, low-mass stars, kind of like our sun when it was a baby. They're often variable in brightness and still surrounded by disks of gas and dust from which planets might be forming. Studying regions like Taurus is absolutely crucial for testing and refining our theories of how stars and planets form.
And just seeing young, massive stars inside or right next to molecular clouds is proof too, right?
Definitely. Those big, hot O and B type stars burn through their fuel incredibly fast. They don't live long enough to wander far from where they were born, so if you see them embedded in a molecular cloud, you know that cloud is an active stellar nursery.
Makes sense. Now, we've talked about clouds in general, but you mentioned different types. Can we break those down? Giant molecular clouds, for instance.
Right, the GMCs, these are the real monsters. The defining characteristic is mass, typically more than 10,000 solar masses, sometimes up to millions. And they're huge, stretching 15 to maybe 600 light years across.
Enormous scales.
Hmm.
And internally complex.
Very. They aren't smooth spheres. They're full of substructure. Filaments, sheets, bubbles blown by stars, and those irregular clumps we discussed.
Filaments again. They seem important.
Increasingly so. It seems filaments are almost everywhere in GMCs. They appear to be fundamental structures. The idea is that gas flows along these filaments, and they fragment into the denser cores where stars actually form.
How do they fragment?
It's likely a mix of things. Gravity pulling denser parts together along the filament, maybe instabilities caused by the filament bending or twisting, and magnetic fields probably play a significant role in channeling the gas and influencing where collapses happen.
And inside these filaments and clumps are the cores.
Yes, the really dense cores, with densities maybe 10,000 to a million particles per cubic centimeter. We trace these with molecules like CO, but also ammonia, NH3, is a good tracer of these very dense regions. Visually, they often appear as dark nebulae because the dust concentration is so high it completely blocks visible light from behind.
Like dark smudges against the starry background.
Exactly. Locally, some GMCs are so big they cover familiar constellations. The Orion Molecular Cloud Complex is a classic example, so is Taurus. They're part of a larger structure near us called the Gould Belt.
And the biggest one in the whole galaxy.
That's probably the Sagittarius B2 complex near the galactic center. It's incredibly massive and chemically very rich. Astronomers often use it as a laboratory to search for new, complex interstellar molecules because there's just so much stuff there.
Okay, so GMCs are the giants. What about smaller clouds?
Those are generally called Bok globules, named after astronomer Bart Bok, who first studied them extensively. These are much smaller, typically isolated clouds.
How small?
Usually less than a few hundred solar masses. They're gravitationally bound, meaning their own gravity holds them together. And while the whole globule is small, their central parts can be just as dense as the cores inside GMCs.
So they can form stars too.
Oh, yes. They often form just one star, or maybe a binary or small multiple system, rather than a large cluster like you get from a GMC core.
Interesting. So different scales of star birth?
Yeah.
And there was a third type.
Yes, the high-latitude diffuse molecular clouds. These were a bit of a surprise, found mainly by the IRAS infrared satellite in the 1980s.
High latitude means away from the main disk of the galaxy.
Exactly, well above or below the galactic plane where most of the gas is concentrated. They tend to be filamentary in shape as well, but much more tenuous, much less dense than GMCs or Bok globules. Typical densities are maybe only 30 particles per cubic centimeter.
So a fainter, more spread out kind of molecular gas away from the main action.
Kind of, yeah. Their role in the overall picture is still being studied.
Fascinating diversity. To wrap things up, maybe list a few more well-known examples of these cloud complexes. We've mentioned Orion, Taurus, SAG-B2.
Certainly. There's the Rho-Ophiuchi cloud complex, another relatively nearby and very well-studied region, famous for its beautiful colors and photos. The Serpens Aquila Rift is a huge dark lane across the sky.
I think I've seen pictures of that.
Probably. Then there's Corona Australis, Musca Cumulonis complex down south, the Vela molecular ridge, the Perseus molecular cloud, and the Radcliffe wave is a more recently identified enormous wave-like structure of interconnected clouds that includes Orion.
A wave of star formation.
Something like that, yes. It shows how these clouds can be organized on even larger scales than we previously thought. Each of these regions offers a unique window into star formation under different conditions.
So it really drives home the point. These dark, cold corners of space are anything but quiet. They're incredibly dynamic, constantly building, churning, and creating the very stars that light up the universe.
Absolutely. They are fundamental to galactic evolution. Without molecular clouds, you simply wouldn't have ongoing star formation as we know it. They are the engines of cosmic renewal.
It definitely makes you pause and think about the sheer scale, the incredible activity happening inside what just looks like empty, dark patches in the night sky. What other secrets about how the universe builds itself are still hidden away inside these vast cosmic nurseries? Perhaps that's something for you to ponder as we continue to explore star formation, the interstellar medium, and the amazing chemistry happening between the stars. Thank you so much for this illuminating deep dive.